August 2nd, 1941. Detroit, Michigan. Inside Packard Motor Car Company's East Grand Boulevard plant, two Rolls-Royce Merlin engines roared to life on test stands. But something was different. These weren't British engines. They were American-made copies, built from British blueprints that Packard's engineers had completely rewritten. The crowd watching that day had no idea they were witnessing an engineering revolution, because hidden inside those engines was a secret that would transform World War II. The bearings were different. The tolerances were tighter. Even the thread patterns on every bolt had been painstakingly replicated from Britain's arcane Whitworth system. Detroit had just turned a hand-fitted luxury engine into America's most mass-produced power plant, and they'd done it by breaking every rule Rolls-Royce held sacred. This is the untold story of how Packard engineers solved an impossible problem, not by winning battles, but by conquering something far more difficult, converting 14,000 precision parts from imperial measurements to American mass production without losing a single horsepower.
In early 1942, the United States Army Air Forces had a fighter they loved and a fighter they couldn't use. The P-51 Mustang, powered by the Allison V-1650 engine, was beautiful at low altitude, fast, agile, deadly below 15,000 feet. But above that, it became a struggling, gasping liability. The problem wasn't the airframe. North American aviation had designed a masterpiece. The problem was physics. The Allison engine used a single-stage supercharger that simply couldn't compress enough air at high altitude. By 25,000 feet, where German fighters operated with ease, the P-51 was down to barely 1,000 horsepower. By 30,000 feet, it was essentially helpless. The cruel irony? American bomber crews desperately needed escort fighters that could operate at precisely those altitudes. B-17 Flying Fortresses cruised between 25 and 30,000 feet on their bombing runs deep into Germany. Without fighters capable of matching that altitude performance, they were being slaughtered. In August 1943, during the raid on Schweinfurt, 60 bombers were destroyed in a single mission. The Luftwaffe knew the Allison Mustang's weakness. They simply climbed above it and waited. What the Army Air Forces needed wasn't a new fighter. They needed a new heart for the one they already had.
3,000 miles away in Derby, England, Rolls-Royce Limited had the solution. Their Merlin engine was powering Spitfires and Hurricanes to altitudes the Allison could only dream about. The secret was a two-stage, two-speed supercharger system designed by engineer Stanley Hooker that maintained sea-level pressure all the way up to 30,000 feet. But the Merlin wasn't just an engine, it was a philosophy. Every Rolls-Royce Merlin was essentially hand-built, 14,000 individual parts, each one fitted by skilled craftsmen. When a connecting rod didn't quite match the crankshaft, a worker filed it until it did. When bearing clearances varied, they were individually adjusted. The British standard Whitworth thread system, with its 55-degree angle and unique radius corners, meant every fastener was custom manufactured. Operating tolerances in the supercharger measured .0001 inches. That's the thickness of a human hair divided by 4. Cylinder heads were individually matched to blocks. Supercharger impellers were balanced by hand. This wasn't mass production, this was art. And Britain couldn't make them fast enough. By September 1940, with the Battle of Britain raging overhead, Rolls-Royce's shadow factories in Crewe, Manchester, and Glasgow were running 24 hours a day. They were producing roughly 200 engines per week. They needed 2,000. The British government looked across the Atlantic. Could American industry help? But what they didn't know was that they were about to ask Detroit to perform an engineering miracle that seemed mathematically impossible. Convert precision craftsmanship into assembly line manufacturing without changing a single dimension, losing a single horsepower, or compromising a century of Rolls-Royce engineering tradition. The real challenge wasn't building engines. It was translating an entirely different industrial philosophy into the language of American mass production. When Rolls-Royce engineers arrived in Detroit in September 1940, they brought crates containing complete Merlin engines, hundreds of blueprints, and unwavering confidence in their methods. The licensing agreement was worth $130 million, astronomical money for 1940. Packard Motor Car Company wasn't an obvious choice. They built luxury automobiles, not aircraft engines. But they had something Rolls-Royce didn't: American manufacturing genius. The moment Packard's engineering team examined the blueprints, they knew they had a problem. Actually, they had about 14,000 problems. First problem, the measurement systems were incompatible. Britain used imperial measurements, but not the same imperial system America used. Rolls-Royce specified dimensions in thousandths of an inch, but their baseline standards came from the British engineering tradition that predated standardization. Converting these to American specifications wasn't simple math. It required understanding the intent behind every tolerance. Second problem, the British standard Whitworth thread system. Every bolt, every nut, every threaded connection used a 55-degree angle thread form with radiused roots and crests. American unified fine threads used a 60-degree angle with flat roots. They weren't interchangeable. Packard would need to manufacture every single fastener in-house using British specifications. Third problem, and this was the big one: Rolls-Royce's tolerances were designed for hand-fitting. When British workers assembled a Merlin, they expected to adjust parts as they went. Clearances of plus or minus several thousandths of an inch were common because craftsmen would make it fit. Detroit didn't work that way. American automotive production required perfect interchangeability. Any engine component had to fit any engine, period. No filing, no adjusting, no skilled craftsman making it work. The British engineers were polite, but skeptical. Could American factories really maintain Rolls-Royce standards? Lead engineer at Packard, Colonel Jesse G. Vincent, gave them a surprising answer: "Your tolerances are too loose for us." The room went silent.
What happened next would become legendary in engineering circles. Packard didn't just copy the Merlin. They reinvented how it could be manufactured while keeping its DNA intact. Over 11 months, Packard engineers created 6,000 new technical drawings. Not because the British blueprints were wrong, but because they were incompatible with mass production. Every dimension was re-specified. Every tolerance was tightened. Every manufacturing process was reimagined for the assembly line. But the real genius was in the details. Take the crankshaft bearings. Rolls-Royce used a copper-lead alloy that required careful break-in and frequent inspection. Packard's metallurgy team, drawing on American aircraft engine research, substituted a silver-lead alloy with indium plating. The silver provided better load-carrying capacity. The indium created a microscopically smooth surface that reduced friction and improved break-in characteristics. British engineers initially objected. This wasn't the Rolls-Royce specification. But when testing showed the Packard bearings actually lasted longer and ran cooler, Rolls-Royce quietly adopted the American innovation for their own engines. The thread problem seemed insurmountable. Packard couldn't just switch to American threads. That would make engines incompatible with British aircraft and spare parts. So they did something extraordinary. They created entirely new tooling to manufacture British standard Whitworth threads to American automotive precision standards. Every tap, every die, every thread-cutting tool was custom manufactured. Packard purchased specialized thread measuring equipment from Britain. They trained American machinists in a thread system most had never seen before. BSW for coarse threads, BSF, British Standard Fine, for precision connections, BA, British Association, for small instrument fasteners. The result? Packard-built Merlins used exactly the same thread specifications as Rolls-Royce engines. You could swap parts between Detroit-built and Derby-built engines without hesitation. But here's what made it revolutionary. Packard manufactured those British threads to tighter tolerances than Rolls-Royce did. Every fastener was precisely within specification. No hand fitting required, perfect interchangeability. Then came the supercharger, the heart of the Merlin's high-altitude performance. The two-stage, two-speed system used two impellers on the same shaft, driven through gear trains. In low-speed mode, the ratio was 6.391 to 1. In high-speed mode, activated by a hydromic clutch, it jumped to 8.095 to 1. Those impellers had to be manufactured and balanced to tolerances measured in 10,000ths of an inch. At operating speed, they spun at over 30,000 RPM. The slightest imbalance would destroy the engine. Rolls-Royce balanced them by hand, skilled workers adding or removing tiny amounts of material until the impeller spun perfectly smooth. Packard developed precision casting and machining techniques that produced impellers so consistently accurate they required minimal balancing. They created dedicated test equipment that could measure dynamic balance while the impeller was actually spinning. The result was faster production and more consistent quality. The intercooler system posed another challenge. Compressing air generates tremendous heat, as much as 205 degrees Celsius. To prevent detonation, the Merlin used an intricate cooling system with passages cast into the supercharger housing and an additional core between the supercharger outlet and the intake manifold. 36 gallons per minute of ethylene glycol coolant, circulated by a centrifugal pump, carried away the excess heat. Packard redesigned the coolant passages for more efficient flow and easier manufacturing without compromising cooling effectiveness. Every single system was analyzed, reimagined, improved for production while maintaining performance.
By August 1941, exactly 11 months after signing the agreement, Packard was ready. The first V-1650-1, Packard's designation for the Merlin XX, ran on a test stand at the East Grand Boulevard plant. Winston Churchill reportedly wept when he heard the news. Britain would get the engines they desperately needed. But making one engine work was different from making 55,000 of them. Packard transformed their factory into a precision engineering marvel. The production line for the V-1650 used dedicated machining centers, each one configured for specific operations: crankshaft machining stations, block face milling stations, cylinder head stations. American automotive mass production philosophy demanded that every operation be repeatable and measurable. If a crankshaft main bearing journal needed to be 2.2495 inches in diameter, every crankshaft that came off the line measured 2.2495 inches, not 2.2492, not 2.2498. Exactly right, every time. This eliminated the skilled hand-fitting that Rolls-Royce relied on. A Packard line worker didn't need years of apprenticeship. They needed good training and excellent machinery. Production ramped up through 1942. By 1943, Packard was producing engines faster than North American aviation could build airframes to put them in. At peak production, the Detroit plant completed approximately 400 engines per week, double Rolls-Royce's entire British output. The V-1653,
based on the advanced Merlin 63 with improved high-altitude performance, became the engine that transformed the P-51B Mustang into the war-winning escort fighter. That two-stage supercharger could maintain over 1,200 horsepower at 40,000 feet, altitude where the Allison wheezed and struggled. The most produced variant, the V-1657, powered the iconic P-51D with its bubble canopy. At 1,315 horsepower at sea level, it could pull the Mustang to 437 miles per hour and sustain combat operations up to 40,000 feet. Those engines escorted American bombers from England to Berlin and back. The Germans called it der Amerikanische Raubvogel and learned to fear the sound of Merlin engines at altitude. By the time production ended in 1945, Packard had built 55,523 Merlin engines, more than all the Rolls-Royce factories in Britain combined.
The Packard Merlin represents something profound in engineering history. It proved that precision and mass production aren't opposites, they're complementary when you understand the underlying principles. Rolls-Royce built exceptional engines through craftsmanship. Packard built exceptional engines through systems. Both approaches worked, but only one could scale to the demands of total war. The techniques Packard developed, precision casting, statistical process control, dedicated tooling for consistent quality, became fundamental to modern aerospace manufacturing. When you fly in a Boeing or Airbus today, the jet engines are manufactured using descendants of the same principles Packard pioneered in 1941. The bearing technology Packard developed for the Merlin influenced post-war automotive engineering. Those silver-lead Indian bearings with their superior load-carrying capacity and reduced friction became standard in high-performance engines. Even the thread compatibility story has modern echoes. Today's international standards like isometric threads exist precisely because engineers learned from World War II that incompatible fastener systems create impossible logistics problems. But perhaps the most important legacy is philosophical. Packard proved that you could honor tradition while embracing innovation. They didn't discard Rolls-Royce's wisdom, they translated it into a different industrial language. They kept the British thread specifications not because they had to, but because engineering integrity demanded it. That respect for interoperability, for standardization, for making systems work together, shapes how we approach global manufacturing today. Several Packard Merlins still fly. The Canadian Warplane Heritage Museum's Lancaster bomber in Hamilton, Ontario, uses 4 original Packard engines. At Reno Air Races, unlimited-class P-51s with modified Packard Merlins produce over 3,800 horsepower, nearly 3 times the original specification. Those engines, built more than 80 years ago, still run, still perform, still demonstrate what American engineering achieved when necessity demanded the impossible.
The P-51 Mustang earned its reputation as perhaps the finest fighter aircraft of World War II. But its secret, the reason it could dominate the skies over Europe, wasn't just the airframe or the pilots. It was an engine designed in Derby, England, and perfected in Detroit, Michigan. The Packard Merlin story isn't about one country's engineering being superior to another's. It's about complementary strengths. British innovation created the Merlin's revolutionary design. American manufacturing genius made it available in the quantities war demanded. 14,000 parts, 6,000 new drawings, 11 months of intense engineering work. The result changed the course of history. Next time you see a P-51 Mustang at an air show, listen carefully to that distinctive Merlin howl.
You're hearing the sound of two engineering philosophies working in perfect harmony. British innovation and American mass production combined to create something neither could have achieved alone. If you found this story fascinating, subscribe to this channel for more deep dives into the engineering solutions that changed warfare. Next week, we're exploring another invisible war winner, the story of how American engineers broke the Japanese Purple Code by building a mechanical computer from scratch without ever seeing the actual machine they were trying to replicate. Hit that notification bell. These are the stories they don't teach in history class because they're not about who won battles, they're about how problems got solved. And sometimes the engineering challenge is more impressive than the battlefield victory.